Welcome back to the Mechanics of Solids lecture series. We're solving examples for bending stress and bending moment of inertia in beams. We're continuing an example we started in the previous video. For the channel sections shown, we're calculating the centroid, the moment of inertia about the z-axis, and the normal stress on the bottom of the flanges due to an applied moment. In the last video, we found the centroidal distance from the bottom reference axis of 27.49 millimeters. We'll continue by calculating the moment of inertia about the overall centroidal axis. In order to do this, we divide the channel section up into different rectangles. The first rectangle being the web on the top, number 2 and number 3 being the flanges on the side. And to calculate the overall moment of inertia, we'll apply the parallel axis theorem, which says that IZ prime equals I for each individual rectangle about its own centroid, plus its area times d squared, where d is the distance from the overall centroidal axis to the centroid of the section itself. And we'll add together the contribution for each rectangle. It's convenient to summarize the calculations in a table. So I'll create a table here for the inertia. We'll label the columns. We'll calculate I in millimeters to the fourth. We'll calculate d sub I in millimeters. We'll calculate d sub I squared times a sub I in millimeters to the fourth. And then we'll calculate IZ prime in millimeters to the fourth. And we'll add together the contributions for each section 1, 2, and 3. Starting with section 1, I for that section, a rectangle, BH cubed over 12, will take B to be 75 millimeters and H to be the thickness 6 millimeters. So we have 75 times 6 cubed over 12, which is 1350. D sub I is the distance from the overall centroid to the centroid of this section, halfway through the thickness. So we can sketch it like that, D1. D1 for section 1 would be equal to 12.51, which is the distance to the top, minus half of the thickness, 3, or 9.51. A sub I, or A1, was 450 from the previous video. So D1 squared times A1 is 40,698. And the sum of the first column and the third column gives 42,048. Now we'll add the contribution for section 2 and 3, which are identical. Section 2, moment of inertia about its centroidal axis, BH cubed over 12, B being the thickness, which is 6 millimeters, and H being the height, which is 40 minus 6, or 34 millimeters. So 6 times 34 cubed over 12 is 19,652. Same for both 2 and 3. D sub I is a distance, or D2, the distance from the overall centroid to the centroid of this section. So I sketch D2 with something like that, this distance between those two axes. Okay. D2 is equal to 27.49, the distance from the bottom reference axis, minus the distance of 17 up to the centroid of section 2, which is 10.49. So that's the same for both 2 and 3. D2 squared times A squared, area of those sections was 204 millimeters squared from the previous video. So the product is 22,448. It's the same for both sections. And then finally adding together the first and the third column gives 42,100. Same for both sections. And the overall moment of inertia is a sum of the numbers in the last column. So 126,000 248 millimeters to the fourth. So that's our answer for moment of inertia. Finally, we have everything we need to calculate the stress. Sigma equals my over I. Sigma bottom equals m times c bottom, the distance from the centroid to the bottom of the section, over Iz prime. Now notice I dropped the negative sign. I'm going to calculate the value of the stress and determine the sign by inspection. Starting with the moment. First of all, I want to make note of my working units. I want to calculate stress in megapascals, so my working units are newtons, millimeters, and megapascals. My moment is given in kilonewton meters. I'm going to convert that to newton millimeters by multiplying by 10 to the 6th. 1.05 times 10 to the 6th newton millimeters. So kilonewtons to newtons by multiplying by 10 to the 3rd, and meters to millimeters is also multiplying by 10 to the 3rd, and that's where I get the 10 to the 6th. The distance C bottom is the same as the distance from the centroid to the reference axis, 27.49 millimeters, and divide by Iz prime, 126 to 48 millimeters, that's a 2, sorry, millimeters to the fourth. And doing the calculation, I would get 228.6. The units are megapascals, millimeters squared on top, millimeters to the fourth on the bottom, reduces to Newton per millimeter squared, or megapascal. Finally, by inspection, if I apply a positive moment, the beam bends upward, makes a smile, the bottom is in tension, the top is in compression. The stress I'm calculating is in the bottom, and so it's going to be a tensile stress. And that concludes this example.